Hey guys, welcome to lesson 2, where we're going to be covering NAND and NOR gates, also commonly known as the universal gates, because the NAND and the NOR can represent the AND, the NOT, as well as the OR gates. We won't go into detail of how to do that until future lectures, because I feel that after we learn the truth table and K-maps, then we can easily do this. If not, then it's going to be a little harder to explain and everyone's going to get confused. So without further ado, we should go into what a NAND gate is. So over to my left here, I have a representation of an AND gate. Over to my right, I have a representation of a NAND gate. So basically, a NAND gate is the opposite of an AND gate. And how you know that is that there's this bubble right here. Okay, this bubble means that whatever the output of an AND gate were to be, this bubble right here flips it around. Okay, if you recall from my earlier video, we described what a NOT gate was, right? A NOT flips whatever the input is. And so that's exactly what a NAND gate does. It flips whatever an AND gate does. Alright, so if we were to represent that with code, we'd simply add this exclamation mark and then two parentheses saying, okay, we evaluate what this expression is inside here, and then we flip it, right? So with this example right here, if A were to be true and B were to be true, that means that the expression inside here would be true as well, which is our representation for an AND gate. However, a NAND gate would be false because we have that exclamation point, right? So, same goes true for all three of these cases. You can simply just put in, if this was true and this was false, then using an AND gate, we know that this would be false, but if we wanted a NAND output, we have the exclamation point, so it's going to be true, right? So you can probably stop this video and, go through all the scenarios yourself, but I won't bore you to death, so we're going to move on to a NOR gate, which is basically the same concept. So over to my left here, I have an OR gate, and over to my right here, I have a NOR gate. Notice how the difference between the two gates again are this bubble right here, right? This bubble represents that the output is going to be flipped. So technically, I should have included this exclamation mark, which I don't know why I didn't. So then right here, this expression inside right here represents a OR gate, and then an exclamation point with two parentheses would represent a NOR gate, right? So basically, we can again go through these scenarios, and then you'll find that the expression inside right here would be a OR gate, and then what it returns is going to be a NOR gate, which completely makes sense. So again, go through these scenarios yourself and then ask me if you have any questions, but I'm pretty sure it's pretty self-explanatory. Alright, so we shall move on to the next item of business, which is universal gates, as I mentioned earlier, that you can use NAND gates and NOR gates to represent any other gate you can imagine. So let's try using a NAND gate to represent a NOT gate. So remember, a NOT gate is a gate that takes in an input and it spits out the opposite of its input. Alright? So how we represent that using a NAND gate is that the NAND gate's always going to have two or more inputs. Okay, it cannot have just one input. That won't work. So notice how a NOT gate has one input. So what we're going to do is that we're going to combine the two inputs of the NAND gate into one using a wire. Okay? And this wire is going to be hooked up to the input, which is A. Now, you're probably like, whoa, that's so genius and smart. And I'm just thinking that's such a hack, but it still works. And so if A were to be 5 volts, right? So we have 5 volts going into this branch as well as 5 volts going into this branch. That would mean that the NAND gate is reading both inputs as 5 volts, right? So, again, the NAND is going to output 0 volts because it's going to be what the AND is, but flipped, right? So if both branches were to be 5 volts, the AND would output 5 volts, but the NAND would obviously output 0 volts. Same goes true if A were to be 0 volts. The NAND gate would read both 0 volts, right? And then since it's the flip of an AND gate, it's obviously going to output 5 volts. And as you can see already, our input, if A was 5, our output would be 0. If A was 0, then our output would be 5. And we've already implemented the NOT gate, right? Whatever the input is, the output is flipped. So in my next video, I'll be going over truth tables, which is another really awesome way of representing these logic gates instead of using true, false, and voltages and whatsoever like that.